Hello everybody, in this lecture we will be solving 1991 IMO problem number 6. Here is a view of this problem. An infinite sequence x0, x1, x2 and so on of real numbers is said to be bounded if there is a constant c such that the absolute value of x sub I is less than or equal to c for every I. Given any real number a strictly greater than 1, we would like to construct a bounded infinite sequence x sub 0, x sub 1, x sub 2, up and so on, such that this given inequality holds for every pair of distinct non-negative integers I and j. This question has a lot of calculus flavor onto it. In fact, we will prove something stronger. I will show that such a sequence exists even for a equals 1. Obviously, if such a sequence where each term is bounded like this exists, then and knowing that I minus j is greater than or equal to 1, I and j being integers, right? So this would make it even larger. So as a result, proving it for a equals 1 is a stronger condition. If I can do that, then the weaker condition will be immediate. The main idea is to consider the fact that root 2 is an irrational number in the sense that it is far from any rational number, and that distance we will try to find a lower bound. So that's kind of one idea, one way to construct such a sequence, because root 2 is very well known and all of its properties, especially the rational approximation of root 2, is very well known. At least consider this. So the distance from any rational number to the irrational number root 2, that distance is equal to finding the common denominator, root 2n minus m over n, for each mn strictly greater than or equal to 1, where m and n are integers. And further, I can write this as, well, we can take out the n because it's positive. So we have this thing here. Finally, now I can multiply both the numerator and the denominator by this positive number, root 2n plus m, and as a result we would get that this is equal to, I can add an absolute value for the numerator, and then putting them under the same absolute value, we will get 2n square minus m square over n times square root 2n plus m. And finally, I claim that the expression on the numerator is strictly greater than, well, not strictly, sorry, is greater than or equal to 1, and for a very simple reason. The power, so it consists of two terms here, the left and the right term. N and m are integers, and I would like to see if this difference can ever be equal to 0. But that won't be the case, as it would contradict, it would violate the irrationality of root 2, obviously, right? So if I create some space here, 2n squared being equal to m squared would imply that root 2n squared is equal to m squared, and as a result root 2n, and that won't work because root 2 times n will not be equal to an integer. So what I'm trying to say, so this thing is never equal to 0. As a result, it's greater than, so the numerator is always greater than or equal to 1, suggesting that this whole fraction is greater than or equal to 1 over n times m plus root 2n. And let me get rid of this part here. Now that we have this result, consider now fix integers I and j greater than or equal to 0, and we can set n equals I minus j and m equals, I propose the following, the floor function of square root 2i minus the floor function of square root 2j. And now notice that m, which is, let me rewrite this thing, square root 2I, floor function, and then the floor of square root 2j is strictly less than 2i, square root 2i without the floor function minus square root 2j plus 1. And it's very easy to confirm this result. You can just move the floors on the left hand side to the right hand side and observe that this whole thing will be greater than 0. So it's easy to confirm this, and that's simply equal to, I can factor out the root 2 here, and I would have I minus j plus 1, which is simply root 2. I minus j was just n, root 2n plus 1, that's less than or equal to, I claim root 2n plus n, because I and j being distinct integers, this thing is greater than or equal to 1, so that's less than or equal to root, which is simply equal to root 2 plus 1, n times root 2 plus 1. If we now add root 2 to both sides of this inequality, therefore, let's summarize what we did here. So m is strictly less than n times root 2 plus 1, and I simply add root 2n to both sides of this inequality, implying that m plus root 2n would be less than, strictly less than, n times 2 root 2 plus 1. And in fact, I can rename this as c, so that would be just equal to c times n. So n plus root 2n is strictly less than cn. Now, also combining everything we got so far into the earlier inequality, so we would get that. So let's go back to this earlier inequality. Let me rewrite it. So therefore, we have found earlier that the absolute value of root 2 minus m over n is greater than or equal to 1 over n times m plus root 2n. And now it's time to plug in all these results that we have just found, and also the expression here which we just collected. So we would get that, so this would imply root 2 minus m was just defined as such here, so root 2i, the floor minus the floor of root 2j, all divided by I minus j, that's n, is strictly greater than or equal to 1 over, replace n with I minus j, and m plus square root 2n with something even bigger, so making denominator bigger will make the fraction even smaller, so that the direction of the inequality will not be disturbed. So as a result, we can just simply replace it with c times n. So c times n was I minus j, so rewriting it nicely, we would get c times I minus j squared. Now doing some cross multiplication and cancelling out the I minus j terms, we would get, so this would imply that, so I can move the c to the front, c times the and then I can find the common denominator, square root 2 I minus j minus the floor of square root 2i minus the floor of square root 2j, close the parenthesis, and the absolute value. The I minus j's would cancel out with one of them. We still have one more I minus j remaining, and that would be greater than or equal to 1. So therefore, the question was to define, construct the sequence, so which would, so this term here. So therefore, this whole expression here is the definition for x sub I minus x sub j. As a result, So this would imply that x sub I can be defined as c times the absolute value, sorry, c times, right, times, because the absolute value is already here, so we are only interested in the interior, so c times the c times square root 2I minus the floor of square root 2I, and for this would work for I equals from 1, no, it would work for any I, so from 0, 1, 2, and obviously with this definition we need to still check that all the xi's are bounded by c, and that's easy to confirm because note that absolute value of xi is equal to the absolute value of c times root 2I minus the floor function of root 2I, and that thing is simply noticing that this guy here is obviously less than 1, so by removing this, I'm removing something less than 1. This will be less than, or if you will, less than or equal to the absolute value of c, but c is a positive integer, so the less than or equal to c for all I, again for all I, and so therefore the condition is satisfied. So as a result, we have found a sequence x sub I such that x sub I minus x sub j times I minus j is greater than or equal to 1, and well, obviously here we defined for I greater than j, which is greater than or equal to 0, and this is a stronger result than the weaker condition with the power raised to the 8th power, where a is strictly greater than 1, because I minus j is greater than or equal to 1. So raising the I minus j further to the 8th power will make it even larger. So therefore this would imply that x minus x sub I minus x sub j times I minus j raised to the 8th power is definitely greater than or equal to 1 for I strictly greater than j greater than or equal to 0, and a strictly greater than 1, and we are done. Hope to see you guys in our next video.